Good afternoon, everyone. I'm Mitsuru Ikeda from Railway Technical Research Institute in Japan. Today, my topic is aerodynamic effects on pantographs on high-speed trains. Today, it's a great honor for me to have opportunity to present these topics in India. First of all, I summarize distinctive feature of pantograph and catenary system for Shinkansen systems. It's because these features have effects on today's my topics. I categorize features of pantograph and catenary system for Shinkansen systems into 3 points, as shown here. One is electrical connected pantographs. Basically, a Shinkansen train has 2 pantographs connected electrically to each other. This achieves suppression of arcing even if one pantograph causes loss of contact. Electrical connection in AC lines can be allowed by using changeover sections of feeding systems. The second point is low mean contact force pantographs. Such pantograph produces a low uplift of contact wires, so risk for serious damage of the catenary is relatively low. The electrical connection between pantographs allows the mean contact force to be low without frequent arcing. The third point is environmental friendliness. The low noise pantograph with electrical connection generates low arcing noise and also low aerodynamic noise. This figure shows the measurement results of standard deviation of contact force between pantograph and catenary on Shinkansen trains. As you can see, due to the aerodynamic interaction between pantograph and catenary, fluctuation of contact force increases with increase in the train speed. If the amplitude of contact force fluctuation becomes greater than the mean contact force, the pantograph cannot maintain contact with the contact wire. So in order to prevent occurrence of arcing, the mean contact force shall also increase with increases in the train speed. This figure shows the mean contact force of 2 types of pantograph for high-speed trains. The red line indicates the target value, which is upper limit of the mean contact force provided by international standard IEC 62486. The blue and green line shows the actual values of the mean contact force of Shinkansen pantographs. As you can see, the mean contact force of these pantographs used for Shinkansen vehicles increase with increase in the train velocities. But too high mean contact force induces abrasive wear on the contact wire or contact strips. Alternatively, too much mean contact force induces electrical wear of contact wire or contact strips due to arcing. That is to say, what is important is to maintain the mean contact force within adequate range. The mean contact force is also known as the uplift force of the pantograph. The uplift force of the pantograph consists of static components and dynamic components. Static uplift force is provided by the riding mechanism of the pantograph. Unusual coil spring or air actuators are used to provide the static uplift force. Dynamic uplift force is induced by the aerodynamic force acting on the pantograph. This force is proportional to the square of the headwind speed against the pantograph and the lift coefficients of the pantograph as shown here. Hence, in order to maintain the contact force within adequate range, aerodynamic design of the pantograph has an essential role. This shows the configuration of some pantographs for high-speed vehicles. The right-hand side is the pantograph used in the TGV trains. As you can see there, under the pantograph head, there are some small wings to adjust aerodynamic force. But the left side hand is a pantograph for Shinkansen lines. As compared with the pantograph for the TGV, configuration of pantograph for Shinkansen is very simple, and it has no wings for adjustment of the aerodynamic force. This is because these wings may induce distinct aerodynamic noise in the high-speed range. The noise standard in Japan is very strict, so such noise generation cannot be acceptable. So by numerical simulations and full-scale wind tunnel test, we found out adequate shape having suitable aerodynamic force properties. Together with the aerodynamic properties of a pantograph, property of the headwind against the pantograph is also important. This slide depicts the airflow around the vehicles when seen in the moving coordinate fixed on the train. Upper one shows the case of open sections, and the lower one shows the case of the tunnel sections. In the open sections, the headwind against the pantograph is almost same as the train speed. But in the tunnel sections, velocity of the headwind against the pantograph increases due to the piston effect of the train in the tunnel. Increase in the headwind velocity in the tunnel has great influence on the mean contact force of the pantograph. Therefore, it is very important to grasp the flow around the pantograph on the tunnel. For this purpose, we conducted two kinds of measurements. One is measurement of velocity of the headwind against the pantograph on the high-speed train. In this case, sensors were installed on the pantograph. The second one is measurement of flow velocity around the contact wire in the tunnel. In this case, sensors were installed on the cantilever in the tunnel. This slide shows the detail of the measurement of velocity of the headwind against the pantograph. We have developed 3-port pitot tube which can be installed on the side of the pantograph head. This sensor can be measured the velocity of the flow around the pantograph head by sensing pressure of 3 ports. These measurements include 2 steps. The first step, in order to check the relationship between headwind velocity and aerodynamic uplift force of the pantograph, concurrent measurement of them was carried out. The aerodynamic force of the pantograph was evaluated by measurement the tension force acting with a tether, which maintained the pantograph head at the height apart from the contact wire. So the pantograph head did not contact with the contact wire. As the second step, for the purpose of evaluation velocity of headwind speed under the contact conditions, measurement of velocity of the headwind was conducted thoroughly. In this step, the mean contact force could not be measured. This figure shows the lift force of the pantograph. In other words, the dynamic uplift force of the pantograph as a function of train speed. The green plots depict the lift force of the same pantograph measured by the wind tunnel. And the red plot means they are measured in the open section. Blue one is measured in the tunnel sections. In the open sections, the lift force of the pantograph increases with the square of the train speed. And these measurement results agree well with the results measured in the wind tunnel. But the data measured in the tunnel sections is not consistent with the tendency of the data measured in the open sections. So in this In the right-hand figures, the lift force of the pantograph is plotted as a function of velocity of the headwind against the pantograph, measured by the method previously mentioned. In this case, all plots are consistent with the measurement data in the wind tunnel. This means that the lift force of the pantograph does not depend on the train speed, but depends on the headwind speed against the pantograph. So this figure shows the measurement results of velocity of the headwinds against the pantograph with the train velocities. Oh, sorry. Oh, I'm sorry. The horizontal axis represents time, and the vertical axis represents velocity of the headwind and the train. The purple line indicates tunnel. The yellow arrows indicate the time when the measurement train is passing by an oncoming train. The blue line indicates the velocity of the headwind against the pantograph, and the green line indicates the train speed. In the open section, velocity of the headwind is almost same as that of the train. By contrast, in the tunnel sections, velocity of the headwind is greater than that of the train. In addition, transitional fluctuation of the headwind velocity can be observed at the entrance and exit of the tunnel, and also sometimes inside of the tunnel. This slide shows detail of measured headwind velocity in the tunnel sections. In the case of these figures, the vertical axis is representing the velocity ratio, which can be defined as the ratio of the headwind velocity divided by the train speed. The red line indicates velocity ratio in the case of the train with an oncoming train. The blue one indicates velocity ratio in the case of the train without the oncoming trains. In the open sections, the velocity ratio is almost 1. On the other hand, the velocity ratio increase and fluctuate in the tunnel. Increase of the velocity ratio in case of with the oncoming train in the tunnel is greater than that without the oncoming trains. But the moment of the oncoming train passes, the velocity ratio approaches to 1 instantaneously. The increase in the velocity ratio inside the tunnel is caused by the piston effect of the train in the tunnel. And the fluctuation of the velocity ratio is induced by the pressure wave propagation in the tunnel. The existence of the oncoming train greatly influenced on the propagation of the pressure wave, resulting in greater influence on the velocity ratio. As detailed waveform of the velocity ratio indicates, one of the most remarkable points where the headwind increase is the tunnel entrance. When the train enters the tunnel, the headwind velocity against the pantograph is strongly influenced by transient behavior of the air around the pantograph. Therefore, the headwind velocity fluctuates. But after the tail of the train enters the tunnel, the headwind velocity is stable with a large value for a moment. The left lower figure shows the velocity ratio at such positions. As you can see, at 300 km/h, the velocity ratio increased to about 1.3 times